We have already completed continuous time convolution, and we know the fact that convolution is used to calculate the output of an LTI system when the input to the LTI system and the impulse response of the LTI system is provided. And in this lecture, I will explain how to perform discrete time convolution. I will first give you the idea of discrete time convolution, and then we will solve one example. So let's move on to our discussion. We are having one discrete time LTI system with us, and the input to this LTI system is Xn, and the impulse response of this LTI system is Hn, and the output of this LTI system is Yn. Now we can calculate the output Yn by simply convoluting the discrete time signal Xn, which is the input, and the impulse response Hn, which is also the discrete time signal. So when we convolute Xn and Hn, we will have the output of this LTI system. Now let's see what we are required to do to have the result of convolution. We need to perform the summation of the product of two signals. The first one is Xk, and the second signal is Hn minus k, and we are required to perform the summation from k equal to minus infinity to k equal to plus infinity. So let's understand what actually we are doing here. We are having two signals Xn and Hn. We will change the variable n, which is the independent variable, by a dummy variable k. Here also we will change the variable n by a dummy variable k, and after this we will have signal Xk in place of signal Xn, and we will have signal Hk in place of signal Hn. Now we will leave alone signal Xk and we will focus on signal Hk. Let's perform time reversal operation on signal Hk. After performing the time reversal operation, we will have a new signal, that is H minus k. And once we have this signal, we will perform another operation, which is time shifting operation, and we will perform the time shifting operation by n. This will give us a new signal H minus k plus n. We can write H minus k plus n equal to H n minus k. Now look at this result. We are having Xk multiplied to Hn minus k. You can see that we have Xk here, and we have obtained Hn minus k after performing the time reversal and time shifting operations on Hk. So the only thing required is to multiply this signal and then perform the summation. So this is what we do in convolution operation when we are dealing with discrete time LTI system and the discrete time signals. Now let's move on to our example, in which we will calculate the output Yn of an LTI system having input as Un and having the impulse response as Un. So the input and impulse response both are unit step sequence. Therefore output Yn will be equal to the convolution of Un with Un, and the convolution is equal to summation k equal to minus infinity to plus infinity uk multiplied with Un minus k. So keeping all these processes in mind, let's begin our solution. We know we are having unit step sequence as the input to the LTI system, and we are having unit step sequence as the impulse response of the LTI system. And from here we can see that we are replacing variable n by a dummy variable k, and both n and k are integers. So let's quickly replace variable n by variable k. This will give us signal uk as the input signal, and the impulse response will now become uk as well. And you can notice one thing, that by replacing variable n by k, there is no effect on the plot of the signal. And now we will leave the input signal as it is, and we will perform the time reversal operation on the impulse response. So we will leave the input signal as it is, and we will perform the time reversal operation on the impulse response. And we know in case of time reversal operation, we simply flip the signal waveform about the y-axis. So flip the signal waveform about the y-axis and you will have the plot like this. So this is the plot of signal u minus k, and therefore we have a new signal after performing the time reversal operation, and upon this new signal we will perform the time shifting operation by n. So let's perform the next operation, that is the time shifting operation by integer n. We will have the waveform like this. You can see that the waveform is shifted towards the left by n, and this is the signal u n minus k. So we have u n minus k and we have uk. Now let's analyze what will happen when we multiply uk and un minus k depending on the value of n. So here is the plot in which I have included un minus k. You can see the pink plot representing un minus k, and I have included uk. The green plot is representing uk. Now let's say n is equal to -1. This means n is less than 0. Now when n is less than 0, it is equal to -1. You can see that the result of multiplication is equal to 0 for all the values of k. For example, when k is equal to 0, you can see that the green plot is having the value equal to 1. This means uk is equal to 1, but the pink plot is 0. This means un minus k is equal to 0. So 1 multiplied to 0 will give you 0. Similarly, for all the values of k, we are going to get 0 when n is less than 0. And we are performing the summation from k equal to -infinity to +infinity. So we have summation k equal to -infinity to +infinity, and as we are having zeros for all the values of k, if you add zeros from -infinity to +infinity, we are going to get 0. Therefore, the output yn is equal to 0 when n is less than 0. Now we will consider the next possibility, and this time n is greater than or equal to 0. When n is greater than or equal to 0, let's take one example of this. N is equal to +2. The plot of un minus k will now shift like this. Initially, you can see that when n is less than 0, when k is equal to 0, un minus k was 0, but now it is 1. Similarly, when k is equal to 1, un minus k is now 1. K is equal to 2, un minus k is now 1. And for the other values of k which are greater than 2, un minus k is still 0. Now let's calculate uk multiplied to un minus k for the different values of k. And we will first consider the case in which k is negative. This means k is less than 0. For example, when k is minus 2, you can see that un minus k is equal to 1, but uk is equal to 0. So 1 multiplied to 0 will give you 0. So for all the values of k which are negative, we are going to get the product equal to 0. And as we are performing the summation, we will add all the zeros starting from k equal to minus infinity to k equal to minus 1. After this, when k is equal to 0, you can see that un minus k is equal to 1 and uk is also equal to 1. So 1 multiplied to 1 will give you 1. So we will add 1. Similarly, when k is equal to 1, again we have uk and un minus k equal to 1. So the product is equal to 1. So we will add 1. Similarly, when k is equal to 2, we have one more 1. And after that, when k is equal to 3, uk is 1, but un minus k is now 0. And it will remain 0 up to k equal to plus infinity. So again, we have so many zeros followed by 1. Now when you add them up, you will get 3. 1 plus 1 plus 1 will give you 3. So I will write down 3 as the output yn when n is equal to 2. So we are having 3 when n is equal to 2, and from here we can say that yn is equal to n plus 1 because n is 2 and we are getting 3. So 2 plus 1 is 3. We will find out the general answer after understanding the fact that it is good to perform the summation from 0 to n, because from 0 to n we are getting the result of multiplication equal to 1 when n is greater than or equal to 0, and all the other values of k which are outside 0 to n are giving us the result of multiplication equal to 0. So we will perform the summation from k equal to 0 to k equal to n, and the summation we will perform is of 1. Let's understand how we are getting n plus 1 when we perform this summation. We are starting from k equal to 0. We are having 1 when k is equal to 0. Then we have 1 again when k is equal to 1. And we will have 1 all the way to k equal to n. K equal to n. Now if we consider this portion of the summation from k equal to 1 to k equal to n, we are adding ones n times. Therefore, we can write 1 multiplied to n. And if we consider this one present at k equal to 0, we will add one more 1. So from here we are getting n plus 1. So in place of summation k equal to 0 to n 1, we can write n plus 1. So this is how the output yn of the LTI system is defined, and we know the unit step sequence un is equal to 0 when n is less than 0, and it is equal to 1 when n is greater than or equal to 0. Now let's multiply n plus 1 to un. When you multiply n plus 1 to 0, you are going to get 0, and when you multiply n plus 1 to 1, you will have n plus 1. Now compare this definition and this definition, you will find they are same. Therefore yn is equal to n plus 1 multiplied to un. Yn, which is the output of this LTI system, is equal to n plus 1 multiplied to un, and yn is the output when input is un and the impulse response is also un. So this is all for this lecture. In the next lecture, we will understand one simple method known as tabular method to calculate the discrete time convolution.